SMBIOS, short for System Management BIOS, may seem confusing at first, but trust me, it's simple once you understand it. In this video, I'll guide you through how SMBIOS works, the tools you can use to interact with it, and give you some neat insights, including how to decode DMI tables. The Desktop Management Interface, DMI, introduced by the Distributed Management Task Force, DMTF, in the mid-1990s, was the first standard for managing and tracking hardware components in desktop, notebook, and servers. DMI provided a standardized framework that allowed software to retrieve information about system components, such as the processor, memory, and BIOS, in a uniform manner. To facilitate this, the System Management BIOS SMBIOS specification was developed. SMBIOS defined a method for system firmware to store and expose management information, effectively serving as the interface between the system's hardware and management software. Initially, SMBIOS was closely associated with DMI and was even referred to as DMI BIOS in its early iterations. Over time, as technology evolved, SMBIOS became the prevailing standard for accessing system management information, and the use of DMI as a standalone standard diminished. Despite this shift, tools like DMI Decode retain their original names, reflecting their initial purpose of decoding DMI tables. Today, DMI Decode remains a valuable utility for extracting detailed hardware information from the SMBIOS tables, providing insights into system components without the need for physical inspection. On system boot, the BIOS takes charge. It initializes the hardware and creates the SMBIOS tables, which are essential for managing the system. These tables contain valuable information about your hardware components like the processor, memory, and BIOS. These SMBIOS tables are filled with structured data, things like serial numbers, the vendor of the motherboard, CPU details, RAM size, and much more. It follows a predefined binary format to ensure the information is consistent across systems. When your system boots up, the Linux kernel parses these SMBIOS tables, typically from memory ranges between 0F0, 000, and 0FFFFF, or from the EFI entry. This is the point where Linux starts using the data provided by SMBIOS. Let's check out a hex dump of the SMBIOS starting point. You'll see the 32-bit signature _S_M at the beginning, which marks the start of the SMBIOS tables. This is how the data is found. We can see on the chart the anchor string is 4 bytes, 5F53, 4D, 5F, which is 4 bytes total. We can see the SMBIOS major version, which is 1 byte 02, and the minor version, which is 06, so it will be SMBIOS 2.6 in this example. Once the kernel processes this data, it makes it available to user space tools. You can access this information through paths like /sys/class/DMI/ID/ or check out details in /proc/CPU info, which includes things like CPU model and memory info. In the DMI Desktop Management Interface structure, each hardware component is described by a specific DMI type and assigned a unique handle. For example, a processor information type 4 entry might have handle 0x004 for CPU1, and it can reference related structures like L1 cache, handle 0x005, L2 cache, 0x006, and L3 cache, 0x007. Similarly, a system information type 1 structure can reference a baseboard, type 2, or chassis, type 3, through their handles, forming a linked map of system hardware. DMI types are numeric identifiers, ranging from 0 to 127, used to categorize and structure hardware information in SMBIOS tables. Each type corresponds to a specific piece of system data, like processor information, type 4, or memory details, type 17. When using DMI Decode, the -T flag allows you to specify which DMI type to query, such as -T4 for processor information or -T processor for a more readable query of the same data. If you enjoyed this breakdown, make sure to hit the like button and follow me for more content. Thanks for watching, and I'll see you next time.